We're given a function f of x and asked to find some information here. One thing, for now I'm just going to assume we know what the first and the second derivative are, and I've printed those already here. A little bit later I'll find those derivatives and go through that sort of at the end in case you want to review how to find those derivatives. But for now I'm just going to assume that we've already found those. So my function here is x to the 1/3 power times x plus 8. And we've got these derivatives already established. So if I want to find where the function is increasing or decreasing, I need to decide where the first derivative is positive and negative. And that's going to happen, it's going to change signs at the critical numbers, which is where the function is either equal to 0 or the function is undefined. So if I set f prime of x equal to 0, well, this one I've got to be a little careful. F prime of x is a fraction. For a fraction to be equal to 0, that only happens when the numerator is 0. So that would say 4 times x plus 2 is equal to 0. That's only going to happen where x is negative 2. It's also possible in this case that f prime of x is undefined. Now, f prime of x is going to be undefined here because this is a fraction when the denominator is 0. So that's going to say that 3x to the 2/3 is equal to 0. If I divide by 3, that would say x to the 2/3 is equal to 0. And then I would take both sides maybe to the 3/2 power, and that's just going to tell me x is equal to 0. So my critical numbers are x equals negative 2 and x equals 0. And so if I think of this on a number line, we'd have negative 2 here, we'd have 0 here, and we've got some intervals we're going to need to check. So from negative infinity to negative 2, from negative 2 to 0, and from 0 to infinity. And so what I'm going to do, I'm going to look at the interval. I'm going to take a test number. I'm going to take 4 times x plus 2. I'm going to take x to the 2/3. And then I'm going to multiply those together to get f prime. Or divide them to get f prime, sorry. So my interval from negative infinity to negative 2, from negative 2 to 0, and from 0 to infinity. I can take test numbers negative 3, negative 1, and 1 maybe. When I plug into 4 times x plus 2, negative 3 plus 2 is negative, negative times 4 is negative. Negative 3 to the 2/3. Well, the 2/3 power, remember the 3 in the bottom, that's the root I would take, and then the 2 in the top, that's going to be the power that I take, right? So I'm going to take the cube root and then square it. So if I plug negative 3 in, the cube root of negative 3 is negative, but then I square it, that's going to become positive. And then to do the derivative, f prime, I take the 4 times x plus 2 and I divide by 3x to the 2/3. So I'm going to take negative divided by positive, and negative divided by positive is negative. If I put negative 1 in for x, I get negative 1 plus 2. That's positive. 4 times a positive number is positive. If I plug negative 1 in, the same thing happens as negative 3. I get the cube root of negative 1, which is negative, but then I square it. And when I plug in 1, 1 plus 2 is 3, 3 times 4 is positive, 1 to the 2/3 is positive, so that's positive there. And so remember what we end up getting then is where this function is decreasing and where this function is increasing. So it's going to be increasing where there was positive derivatives. So my positive derivatives here are between negative 2 and 0 and between 0 and infinity. It's going to be decreasing where the derivative was negative, that was from negative infinity to negative 2. Now, if I'm looking for minimum and maximum values, it's decreasing from negative infinity to negative 2, and then it changes to increasing negative 2 to 0 and 0 to infinity. So if it changes from decreasing to increasing, that's a local minimum. It never changes from increasing to decreasing, so there's no local maximum. So I'm going to have a minimum it's decreasing from negative infinity to negative 2, and then it changes to increasing at negative 2. So at x equals negative 2. To find my y-coordinate, then, I'm going to have to go back to the original function, f of negative 2. Remember, the 1/3 power is really the cube root. So this would be the cube root of negative 2 times negative 2 plus 8. How you write this is sort of up to you. I know the cube root of a negative number is going to be negative. Negative 2 plus 8 is going to be 6. The easiest way to write this would really just be to say maybe negative 6 times the cube root of 2. I can take that negative out because it's going to be negative overall. And so that's my local minimum value right there. And we already found where it was increasing and decreasing. For concave up and concave down, I do the same sort of thing, except I look at the second derivative, where the second derivative is equal to 0. So that's going to be where the numerator, again, for the second derivative is equal to 0. So that's going to be at x equals 4. And then I also want to look for where f double prime of x is undefined. Since it's a fraction, that's where the bottom is going to be undefined. Divide by 9. Take the 3/5 power of both sides. And I just get x equals 0. So I form my number line and my intervals. And I do a sign chart just like I did up there. So my numerator is 4 times x minus 4. My denominator is 9x to the 5/3. I don't really have to worry about the 9. And then I'm going to divide them to get f double prime. So I've got from negative infinity to 0, from 0 to 4, from 4 to infinity. So my test numbers may be negative 1, positive 2, positive 5. If I plug negative 1 in, negative 1 minus 4 is negative, so that whole thing is negative. Now here I've got x to the 5/3 power. Remember then, the denominator is the root, the numerator is the power. So I'm going to take the cube root of negative 1, which will be negative, and then I'll take the 5th power. A negative number to a 5th power is still negative. And now for the second derivative, that's going to be this quotient, right? The quotient of those two. Negative divided by negative is positive. So it's going to be concave up there. If I plug 2 in for x, 2 minus 4 is negative. Negative times 4 is negative. 2 to the 5/3, well, again, that's going to be the cube root of 2, which is positive, and then a positive number to the 5th power will be positive. A negative divided by a positive is a negative. And now if I plug 5 in, 5 minus 4 is positive. Positive times 4 is positive. And a positive number to the 5/3 power will be positive, so I'll get positive there. And so this is concave up, where I have positive intervals, so that's negative infinity to 0, and from 0 to 4. It's going to be concave down, where I had a negative second derivative. Oops, messed up. Concave up is where it's positive, negative infinity to 0, but then 4 to infinity. and then it's concave down where it's negative, which was 0 to 4. Points of inflection then are where it changes concavity. So it starts from negative infinity to 0, it's up, then it changes to down from 0 to 4, it changes back to up at 4. So I'm going to have to look at x equals 0 and at x equals 4. So I'm going to have to plug in to my second derivative, or I have to plug these values into the original function. So I go back 0 to the 1/3 times 0 plus 8. That's just going to be 0. And I plug in 4. I'm going to get 4 to the 1/3 times 4 plus 8. That's going to be 12 times the cube root of 4. So I get 0, 0. And I get 4, 12 times the cube root of 4. All right, now if we look at this and we want to try to put this together and look at an overall graph, what I've done here, I went ahead and I plugged in that relative minimum point that was negative 6 times the cube root of 2. If I do that on a calculator, I get about negative 7.56. Let's see, so let me write down the concavity. I didn't write that down here. So it was concave up from negative infinity to 0 and from 4 to infinity. It was concave down from 0 to 4. And of course we have the point 0, 0 is an inflection point. So if we're going to try to sketch this graph, oops, I need a pen. All right, something like that. We've got a relative minimum at negative 2. And we had, it was concave up to 0, and then we have an inflection point at x equals 4. So we've got that this function is decreasing from negative infinity to negative 2, and my point down here at negative 2, it has a y-coordinate that's approximately negative 7.56. So somewhere a little above negative 8. It's decreasing from negative infinity to negative 2. And we also had, though, that it was concave up from negative infinity all the way to 0. So it's decreasing, but it has to be bowl-shaped up as it's going from negative infinity to negative 2. So something like a parabola like that. Now from negative 2 to 0, it's increasing, but it stays concave up from negative infinity to 0 as well. So it's going to come up like this and hit this point 0, 0, which we know is on the graph. Now, at 0, 0, it changes, it stays increasing, but the concavity changes to concave down until I get to 4. And it stays increasing all the way now from 0 to infinity, right? We only had the one part where it was decreasing. It was just decreasing here from negative infinity to negative 2. It's going to keep increasing forever now, but I've got to sort of look at this concavity. What happens here at x equals 0 is it changes to concave down. So it's going to do something like this and then start doing concave down. It still stays increasing all the way up here to 4, and then at 4 it changes to concave up again, so it does something like that. It might be hard to see that on an actual graph. We might be exaggerating it a little bit here. Notice at this point, if I drew the slope of the tangent line here, it would be a vertical tangent line. That fits in. That was a place, that critical number actually was where the function was, the derivative was undefined. And that's corresponding to that vertical tangent that we have here. This was the other where my tangent line was horizontal. And so this is what that graph would look like. Now I'm going to go back and at this point, if you can do the derivatives on your own, you don't have to watch the rest of this video. I'm going to go to page 2 and calculate these derivatives so you see how I would get those. We're going to ignore this stuff here at the beginning. I didn't need those. I put those directions somewhere else. So I'm just going to go to my original function, which was f of x equals x to the 1/3 times x plus 8, and we're going to take the derivative of this function and then the second derivative. So to take the derivative, I'm going to have to use the product rule here. So the product rule says I take the first factor times the derivative of the second. The derivative of x plus 8, well, the derivative of x is just 1. The derivative of 8 is 0, so it's just x to the 1/3 times 1. So that's first times the derivative of the second. Then I have to do plus, I have to do second times the derivative of the first. So second, x plus 8. The derivative of the first, I bring the 1/3 down. And now I have to subtract 1 from that exponent. So I have to do 1/3 minus 1. That would be 1/3 minus 3/3. So that would be negative 2/3. And so what I get here then is x to the 1/3 plus 1/3 x to the negative 2/3 times x plus 8. I think the easiest way to get this nicer and get rid of that negative exponent is to write this whole thing over 1 and then just multiply by whatever you need to get rid of that most negative exponent in the top. So I want to get rid of this negative 2/3. I want to change negative 2/3 into 0 because anything to the 0 power is just 1. So I'm going to multiply by x to the 2/3 in the top, but whatever I do in the top I've got to do in the bottom. And now that has to get distributed to both parts. So when I take x to the 1/3 times x to the 2/3, that gives me x to the 3/3, which is just x to the first. Oh, I forgot something here. I also would like to get rid of that 3 in that 1/3, so I'm going to stick a 3 in front there too. So that's going to give me a 3x to the first. Okay. The reason I did that, now when I multiply 3 times 1/3, the fraction goes away. X to the 2/3 times x to the negative 2/3, that gives me x to the 0, which is just 1. So all I'm left with here is just 1 times x plus 8. And then I just get this 3x to the 2/3 in the bottom. So that's going to be 4x plus 8 over 3x to the 2/3. Okay, so that's where this first derivative comes from. To do the second derivative, I'm going to take the derivative of that. Now, this is a quotient, so I'm going to have to use the quotient rule. Let me move down just a little bit more. So the quotient rule, I have to take the bottom times the derivative of the top. So the bottom, 3x to the 2/3. So bottom times the derivative of the top. The derivative of 4x plus 8 is just 4. Minus top times the derivative of the bottom. Well, to do the derivative of the bottom, I'm going to have to bring this 2/3 down in front. So 2/3 times 3, and then I'm going to get x, and it's going to be 2/3 minus 1, so that'll be 2/3 minus 3/3, so that'll be negative 1/3. And then I get the bottom squared. So, what do I have here? 4 times 3 gives me 12x to the 2/3. Here, the 3's cancel. So I get minus 2x to the negative 1/3. And then I get 4x plus 8. All right, I think I've got everything here, right? 4 times 3 is 12. X to the 2/3 goes along for the ride. These 3's canceled, so I bring down the 2. I've got that x to the negative 1/3, and I've got the 4x plus 8. When I square in the bottom, 3 squared is 9. If I square an exponent, I multiply. 2/3 times 2 would be 4/3. All right, now, same sort of thing. I want to get rid of, oh, I didn't want that. I want that bar, but I wanted a little more space. I want to get rid of this negative exponent, so I'm going to multiply top and bottom by x to the 1/3. I don't have any fractions to get rid of, so that should work out fine. And then this has to get distributed, to both parts. So I'm going to get 12x to the 2/3 times x to the 1/3. That's going to be 12. And then, again, x to the 2/3 times x to the 1/3 would be x to the 3/3. That's just x to the first. Minus the 2 goes along for the ride. X to the negative 1/3 times x to the positive 1/3. That gives me x to the 0, which is just 1, so that goes away. The 4x plus 8 stays. And so here then, if I just do a little, we would need to distribute and combine like terms. I'm just going to do that in my head. 2 times 4 would be 8x. 12x minus 8x will just be 4x. Negative 2 times positive 8 is negative 16. And we get 9x to the 4/3. So there was my first derivative, and there's my second derivative. And that's how I got those values at the beginning of the problem.